last class we have studied about discovery of electron, discovery of protons. Discovery of electrons is attributed to cathode rays, discovery of proton is to anode rays. Remember, protons, all anode rays are protons only if the gas inside is hydrogen. Any other gas, it's not proton. Whereas cathode rays are always electrons, right? Discovery of electron is attributed to J.J. Thomson. Discovery of proton is attributed to Eugen Goldstein. And after that, Thomson gave you the model of the atom, which is known as the plum in the pudding model. These questions are mandatory, they will ask you, or it can be also compared to that of a watermelon. And the primary thing that you should understand is the atom has a sphere which is positively charged sphere, and electrons which are negatively charged particles are spread across. Just like plums, pieces of plums are spread across a pudding, similarly electrons are spread across a positively charged sphere or the seeds of a watermelon. Then came Rutherford's gold leaf experiment. Okay, before we proceed to Rutherford's gold leaf experiment, though in your book it will be covered as particles and all, we need to understand something called, just understand, this is not there in your syllabus, but if you don't understand this, then you will start questioning what was that particle, what is this particle. Okay, everything that we are studying here is a part of nuclear chemistry, and these are nuclear reactions. What is the difference with chemical reactions? In a chemical reaction, an atom does not change, it just combines with magnesium, becomes magnesium oxide, but magnesium remains magnesium. Whereas in nuclear reaction, the atom will convert, like a carbon might convert into a nitrogen, a uranium might convert into a barium. Okay, so these, because the entire structure of the atom changes, nuclear reactions are therefore completely different class. The entire person changes. Now, one phenomenon which was earlier in grade 9 but not taught, that you should understand, is what is known as radioactivity. Radioactivity. Now, this is also a accidental discovery. Radioactivity's discovery is attributed to Henry Becquerel. So what Henry Becquerel saw, that he had what you call camera films which were there in his drawer, desk drawer, and certain substances, and because you all are not habituated with camera film, so you have to first make you understand what is a camera film. You all see digital cameras. In our days, cameras used to be loaded with films, and this film loading happens in dark room. You can't load it in light. Yeah, so it will be red room or dark room, we say. When at home also, when we used to load, we used to switch off the light and load it, right? Or else, suppose you are shooting at any historic spot, like in our days, you're shooting at Taj Mahal and your films are over. So you will see people who are roaming with films, Kodak and all you can buy. So if you load it in dark, you get some extra, like these rolls are available with 36 exposures, means 36 pictures you can click. But if you're loading, if you are efficient in loading, you might get 2-3 extra shots also. 39 तक आ जाता है. तो आपको dark में load करना पड़ता है. You have to load it in dark. Otherwise, the film gets exposed. The word we use is exposed, means light will come and touch the film and damage the film. So no light can, and once the camera is closed, no more shut, means opening it till the entire roll has been used. So photography used to be a surprise, not like nowadays that you click and show somebody and then you delete. So in our days, photography was an expensive thing. You just click a picture, and studios used to give you the photo next day, because they used to again open the roll, cut out that much of a portion, but they will charge you 3 times because they are cutting out. But in our case, once all 36 are over, then only it goes for processing, right? So camera films get exposed when they are actually in what you call as any light source. Even when you go for an X-ray, your X-ray film will be in a metallic plate, and that metallic plate is inserted. Okay, so and the film is inside. So Henry Becquerel was actually having some films in his drawer, and these films surprisingly got exposed. Started making him think, what made him get exposed? Why did it happen? Then he saw that there are certain items that he had kept, certain chemicals, which we nowadays call as radioactive in nature. Means these items emit invisible radiations, which you can't see. Just like when we go for an X-ray in any what you call diagnostic clinic, we can't see the X-ray. And I don't know if you have undergone an X-ray. During the X-ray, only you will be in the room, you and the machine. Even the operator will get out of that room and he will be wearing his gear, and he will be in a different room, because otherwise he is prone to radiation. So radioactivity for us to understand is it's a spontaneous emission. Spontaneous emission of invisible radiation. Invisible radiations, okay, from certain atoms, not all, certain atoms, from certain atoms, and then these atoms will be known as radioactive atom. Radioactive atom. For example, uranium, plutonium, thorium, radium, carbon-14. Carbon-14 is also radioactive. Spontaneous emission of invisible radiation. Invisible radiation means the word radiation is equivalent to energy. Here all the stories will come out here. It's a release of energy. Understood? All energy that is released, right? This energy, and if you go by Einstein's concept, then energy and mass, energy is correlated to mass. Now, how do you understand this? This is what it comes to, that E equal to mc square relation. So it says, if the entire world's energy can be brought and compact in one place, you give rise to mass. And when mass disintegrates at the speed of light, it creates energy. Have you understood? And energy can be converted into one form or the other. So even if you go back to say Mahabharata days and you think that if the battles were fought, then somebody has spoken something that is converted into some form. Maybe today it might sound ridiculous to us, but in near future, somebody might be able to retrieve that energy and get it back. 100 years ago, if you tell anyone that, after death, we can no more have any remembrance of someone apart from his portrait or say picture. Today, you can have all video shots of the person when he was alive and you can see him. So it's all possible, right? So energy is equivalent to mass. Now there is loss of energy. When the loss of energy happens, mass loss will take place. Now, spontaneous emission of invisible radiations. These invisible radiations happen in three norms. Number one is known as an alpha particle. An alpha particle. This will be what we will study in this Rutherford's experiment. Next is a beta particle. Next is a beta particle. And the third is gamma radiation. Gamma radiation. Let's understand all these three a little bit. Alpha particle is denoted by the symbol like this. This is alpha particle. Beta is a B with a long stem, and gamma is written in this manner. There's a gamma particle. Just pull it, and now these two are called particles. These two will be particles, and this is only a radiation. Gamma is neutral and gamma is just a radiation. An alpha particle is a positive particle, a beta particle is a negative particle, and gamma is neutral. Actually, after releasing alpha particle, all these will be released immediately. If you have a radioactive isotope, it goes on releasing these radiations, and they're harmful for you also. So they'll go on releasing these radiations, and these radiations will be spontaneous emission. You need not give any energy or something. Why this happens, we don't know. Unstable nucleus, spontaneous emission will happen. Alpha will be a positive particle, beta will be a negative particle. After that, there will be some stabilization. That stabilization is done by gamma particles. Extremely cancerous. They can penetrate inches of concrete also. Whereas alpha particle we will see now, and beta. So beta is like an electron which is having a negative charge, but the mass is zero. The mass is almost zero. Our thing is to understand about alpha particle. Now let's see what is an alpha particle. To understand alpha particle, we should first understand the helium atom. Helium atom. Alpha is not helium. Many children think alpha is helium. No. This is the closest match by analogy. Let's see what is helium. Helium is somebody whose atomic number is 2 and mass number is 4. Got it? That means helium as a nucleus will have 2 protons and 2 neutrons, and out here it will have 2 electrons. This is the structure of, right? This is an electron and this is an electron. If you take out these 2 electrons, from helium atom, theoretically, then it becomes He 2 double plus. Have you understood? Helium becomes two positives, two negatives gone, so the two positives appear. It's no more neutral. An alpha particle is similar to this. That means an alpha particle has two positive charge, and it will have, so I can write it like this: an alpha particle is someone who has two positive charge and has a mass number of 4u. Why? Because it is the helium atom whose two electrons have been lost, so the nucleus is retained. The nucleus has got two protons, two neutrons. So what is the mass number? 4. So we call an alpha particle, the name that we say is, an alpha particle is a doubly charged helium nucleus. Sir, do you mean to say that alpha was a gas? No. He looks most likely to this. To explain alpha particles becomes difficult. There's no relation between helium and alpha particle. But if you would have taken a helium, yes, if you would have taken a helium, what you call an atom, and if you would have ripped it through its two electrons, then the helium atom becomes a helium ion, which is two positive charge and 4 mass number. An alpha particle is just like that. An alpha particle has got two positive charge and it has got 4 mass number. Therefore, in higher grades, we study something which is called alpha decay. I am an atom. I lost an alpha particle. I'm radioactive. I lost an alpha particle. These are advanced chemistry to understand. I'm an atom. I'm radioactive. I lost an alpha particle. So that's called an alpha decay. When you lose a tooth, it's called a tooth decay, alpha decay. So what is the impact on me? Two positive charges will be gone from my side, not two electrons. Alpha decay means you are taking one alpha particle out of me. So you have taken out two positive charge and my mass number reduces by 4. Here helium concept nahi aata hai. Try to understand, okay? I am a alpha particle. An alpha particle is shown as somebody with 4u and 2 plus. You have a radioactive atom. I have a radioactive atom. You have to understand these concepts. These radioactive atom undergoes something which is known as a alpha decay. It loses an alpha particle. So what will be the impact on this? Its charge, 2 plus charge loss will take place. That means 2 negative charges will become extra. And the mass number reduces by 4. This is just for your understanding because you lost an alpha particle. Whereas if you lose a beta particle, at that case your negative charge loss is 1, mass loss does not take place. Okay? समझ में आया? So our topic will now, we will be discussing on alpha particle. So let's understand an alpha particle. What is the property of an alpha particle? An alpha particle is released during a radioactive emission, and an alpha particle has 2 units positive charge, right? And has a mass number. His relative atomic mass is 4u, 4 atomic mass unit. That means this particle is very heavy. Motu hai ye bahut, very heavy. That's why alpha particles penetration is not that much. Alpha particle can only penetrate up to cardboard, some few centimeters of of cardboard. It's heavy, slow moving particle, but it is heavy. Understood? We will be using this alpha particle because your book will say that gold was bombed by alpha particle. Now you'll not understand what is alpha. So alpha particle is one of the particles which is released during radioactivity. What is radioactivity? Spontaneous emission of invisible radiations by unstable atoms. And these invisible radiations are in 3 forms. If an alpha is released, beta will be released, gamma is also released. By the way, you can also get alpha particle generator sources are also there, like cesium atoms and all. They can only generate alpha particles. Okay. So then there is an atom called americium. In Americans call it americium, Russians have a different name. So that can also generate only alpha particles. Only, yeah.
All radioactive, most radioactive atoms release alpha, beta, and
radioactive means there will be release of these. Something may be more, something may be less. But you get only two alpha particle generators are also available. I think cesium is one, Americum 298 is one. It releases only alpha particle. So let's go back to our experiment now. The gold leaf experiment. Okay. So as the name says, the name of the experiment is gold leaf. Gold leaf. Now this gold leaf is comparable to when you open Cadbury's Dairy Milk, you get that golden foil. It's just exactly similar to that. Okay. And why gold is chosen? The reason is gold has a very high atomic number. So the chances of gold having new electrons and protons in those days are high. Gold's atomic number is very, very high. So you have a gold leaf. This is like a thin gold leaf. Okay. Gold leaf, just like your Cadbury's Dairy Milk. Now, this gold leaf is actually bombed by a alpha particle which is actually kept inside a lead box. Lead is supposed to absorb all radiation, and this is going to release. This releases alpha particle. Is this fine? And then in the same experiment, what they did, they also kept a screen out here, and this screen is coated with zinc sulfide. Zinc sulfide is fluorescent once it gets a particle hit. So the alpha particles are bombed in this manner. Okay, so these are alpha particles which will be bombed, and if you get an impression on this side, it means the alpha particle has torn apart the foil and has actually gone. By eyes you cannot make out anything, we can only see by impression. But these are very calculated experiments where you can find out how many units of radiation you have resolved. So when they did this experiment, they actually found three observations. Like if I'm releasing X numbers, okay, say I'm releasing X numbers of alpha particle. The first observation is, first observation was majority of alpha particles pass through the foil. How did they get to know that it passed through the foil? Because they got impressions on this side of zinc sulfide screen. Is this understood? Second observation they saw was very few were deflected from their path. Means these are particles, these are being bombed, alpha particles. So we have to understand the experiment. A thin strip of gold is taken, foil of gold, and it is bombed by a stream of alpha particles. As the stream of alpha particles go and hit, three observations were made. First observation was majority passed through the foil. A very few got deflected. And the third is very, very few. Something like 1 in a million was rebounded 180 degree. These three things you have to understand and get it. Now we'll see what happens, why this happens. Many, very less amount of them got rebounded, and that was like 1 in a million. Majority passed through, very few got deflected, and very rare of the rarest, few got 180 degree rebounded. Okay, so let's try and see what exactly happened to find the give a what you call, we have to give an explanation for whatever thing happened. Okay, so let us take a gold atom now. This is a gold atom, right? So these are the gold atoms. What are these? These are gold atoms, right? And let's reconstruct our drawings of the alpha particles the way it actually happened. So let's show the alpha particles like this, and let's first create a screen. So we have to have a screen. So let's say this is our screen. And let's go and create the bombing of the alpha particles. Okay, now just to show you. Okay, let's see. Our findings are majority of them pass through. Now this is very interesting. Now this one qualifies for the pass through. Majority, right? And as I write this, I also keep what you call the J.J. Thomson's model also. In J.J. Thomson's model, it is said that the atom is a positively charged sphere, right? The entire atom is positive, 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 positive. The atom is fully positively charged, right? And the electrons are embedded like pieces of plum in a pudding. Now keep this model and start seeing your findings, right? If the atom was completely a positively charged sphere, then how is it possible? These are what? These are alpha particles which are equivalent to doubly charged. If positive particle is entering a positive sphere, how can it pass through? It should repel. It should repel. Thomson says that the entire model is actually, it's a positive sphere. So if we found that majority of them went through, are you understanding? Therefore, the first conclusion that comes from this is that the major space inside an atom is empty. सीधी बात है. Otherwise, my alpha particle should not have gone through. Just passes through. So they are empty, right? Then these are my very few that got deflected. Do you agree? Very few that got deflected tells me there is presence of positive charge in the atom. There is presence of positive charge. That's why it must have gone near a positive charge, it has got deflected. Otherwise, it happily goes through, right? And this was that 1 in a million had what? A 180-degree rebound. Now ask yourself, you play carom so much. How do you get the rebound of the strike? You hit the strike on the bar. The bar is much more harder than the striker. That's why it is able to send the striker back. Otherwise, it should have got an impression on it, hit impression. That means this gives us one more thing. Plus, it's a rebound. It's a rebound. So it says there is presence of a dense packed mass in the atom in a very small region, and it's packed with positively charged particle. See, proton was known. Before he did this, proton was known. And protons were supposed to be much more heavier than electron. So you getting rebounded back, and that too 1 in a million, means that zone which is there is very, very small. But it's small, but it is very compact, that if you hit it, you undergo a complete 180 rebound. Okay, and there is presence of a dense packed mass in the atom in a very small region. Later on, this is compared like a pea in a stadium. This much is actually the comparison. The atom is compared like a stadium, and this is like a pea grain or a seed, a pod of pea, that much, so small that if you go and hit that, that's why 1 in a million ray, that was such an unlucky ray that particular radiation, when it struck that, and it came 100-degree rebounded back. So now this entire model goes for a toss now. First of all, what is the drawback of Thomson's? The drawback of Thomson's model is actually, first of all, you should understand what is the finding of Rutherford. Finding is actually seen in my previous slide. The findings are very simple, that majority pass through the foil. What is the conclusion from this? That major space of the atom is empty. Very few got deflected, means there is presence of positive charge inside the atom. And third is, a 1 in a million came 180-degree rebound back. That says that there is a presence of concentrated mass, right? And that concentrated mass is packed positive charge only. That's why you are rebounding. Had you been electron, you should have absorbed that particular radiation, right? So it says that there is a presence of a dense packed mass in the atom in a small region, and it is packed with positively charged particles. Understood? Based on this finding, this is called the gold leaf experiment. This is all about gold leaf experiment. Rutherford starts giving his model of the atom. So now we get into the Rutherford's model. So what does the Rutherford's model? First is the gold leaf experiment. Finding of the gold leaf experiment. Findings correlated to inferences. Findings are different. An experiment gives you a finding, and the finding will give you inferences which you will pick out. Like the finding is what? Rays pass through. What is the inference? Major space of the atom is empty. Rays got deflected. Inference, atom contains a positive charge. Protons are present. Rays, very few came 180 rebounded. There is presence of condensed dense mass. Okay? No, fine.
लग गया सर, हम पानी का पानी
ये मैं मंगवाया नहीं कुछ। और बेल बजाने से पहले इतना बड़ा बड़ा कर दिया। हाँ, अभी इस बार गलत घर मत बजाइए, दूसरा आदमी मेरे जैसा दयालु नहीं भी हो सकता है। हाँ? The line of the bottom says there is a presence of a dense packed mass in the atom in a very small region, and it is packed with positively charged particles. इसलिए आप बाहर आए। हाँ, कुछ बोले बेटा? ठीक है, चलिए आगे। So from this, Rutherford will now give his model of the atom. So findings are major space is empty, that we have said. So now we come to the Rutherford's model. Rutherford's model of this is part of gold leaf only. From gold leaf you are able to give another. Cathode ray gave the model of Thomson, and there is a presence of a dense packed region. This, what do you call as dense packed mass? This is what for the first time the word was coined as nucleus. Rutherford coined the word nucleus. Before this, there was no word of nucleus. So let's see what is the Rutherford's model. Okay, Rutherford's model says the atom primarily has large vacant space, and my wordings may differ from your book, but they'll mean the same, and all its mass is concentrated in a small region in the center, and this region is called the nucleus of the atom. The atom primarily has large vacant space and all its mass is concentrated in a small region in the center, and this region is called the nucleus. And this small region, you should always remember, P in a stadium. It is that small. That means another takeaway is the nucleus contributes to the mass of the atom. Means that mass of the atom is right there at the center of the atom, which is the nucleus, and the nucleus primarily contributes to the mass. Second, the nucleus consists of protons, or your positive charged particles, packed closely into a small, dense and compact mass. So what did he say? He said two things. One is that the major part of the atom is absolutely vacant, and the atom's mass is all concentrated at the center, and the center is termed as nucleus. It is a compact, dense, positively charged body which is comprising only of protons. तभी हमें दूसरी चीज पता नहीं था. And the third one was he has to accommodate the electrons also. Electrons orbit around the nucleus just as planets orbit the sun. And so his model was better known as the planetary model. So the plum and the pudding model now goes into the trash. And now the atom's model that we have is the atom has a positively charged, dense, compact center, which is known as the nucleus, and the nucleus contains only protons. And around these protons, what do we have? We have electrons that actually orbit this. What do you call? Electrons are electrons, and electrons are orbiting the model. This is known as. छोड़ दो, आपको समझ में, आपको स्टोरी समझ में आया? कौन सा लाइन बोलो? छोड़ दो, आप सोचो. You forget it. These are my words now. My words may be different from the book. Have you understood what did Rutherford say? What all three things did he say? Number one, there should be just English wise correct. One, the major part of the atom is a vacant space, and all the mass is concentrated at the get the words correct. Major part is vacant and all its mass is concentrated at the center in the form of a compact, dense body which is positively charged. He coined that body as the nucleus. Listen to the story. That's why you all are more eager to write. Therefore, you feel that if you're mismatching my words, you're getting something wrong. Nothing wrong. You should understand. Major part of the atom is vacant. All its weight is attributed to its center, which is absolutely a compact, dense region, positively charged, and he termed it as the nucleus. And the nucleus rests all the protons of the atom. Can you write in your own words? Don't worry about that. I will deliberately not show this slide. I'm super crook. Now you write. You put your words. Then only you'll learn how to write. Remember, three things that should come up. That major portion is vacant. All the mass is attributed to the center in the form of a dense, compact, positively charged region. What is the name of that region? Nucleus. Nucleus comprises of protons. Now he has to also accommodate the electrons. The electrons orbit around the nucleus just as planets orbit the sun in a solar system. And hence his model was known as the planetary model. So plum and pudding on. Now you are in planetary model. After this, you have to now learn also what is drawbacks of Rutherford's model. I never like to use the word drawback because they are so big, great scientists. You should never use. Limitations is something because only then you learn. डायग्राम खुद बनाओ, न्यूक्लियस बनाओ अपना, समझे तो हो ना. न्यूक्लियस, छोटा सा न्यूक्लियस बनाओ. तुम पहले लिखे हो कि कॉम्पैक्ट डेंस, then how can your nucleus be so big? Now she has made the nucleus inside. Good. And so in that nucleus, label it. The center part you label nucleus, positively charged, star star, asterisk, positively charged, asterisk, contains protons. Contains protons. Then only you will remember. This is learning. Contains protons. And out there you put electrons. Put one more orbit. Yeah, like that, or you can crisscross it. Then it looks more stylish. This is what you missed. You can see it now. Then it looks more stylish. Yeah. It is three-dimensional ना बेटा, ऐसे ऐसे घूम रहा है ना पूरा. हाँ. अभी देखेंगे वो ड्रॉबैक देखने के लिए फिर एक नया चीज समझ. ड्रॉबैक्स में डायग्राम नहीं है. Drawbacks, for drawback we have to understand another one phenomenon, just like you understood radioactivity. Radioactivity is not in your course. If you don't understand radioactivity, you don't understand what that goddamn alpha particle is. Alpha particle comes from a radioactive source. Now understand the drawback. You have to understand something of electricity and radiation, which was actually derived much before this thing, and that was done by another great scientist whose name is James Clerk Maxwell. So you have to understand one Maxwell's finding now. Then only we will understand the drawback. Very few, 1 in a million. Deflected a little, they show the presence of positive particle. I don't like this fellow, suppose. So when I'll come near him, I'll just deflect away. Na? No, it will not touch the nucleus. You cannot touch the nucleus is all positive. How can a positive particle go and touch the nucleus? You will always deflect. It's like a magnet. And suppose I have bombed you straight 180, then if you have gone there, you will be rebounded back very badly. Alpha particle, please understand, alpha has mass. Therefore, alpha was taken. They didn't do it all this with beta or other positive particle. They didn't do it with a stream of protons. Alpha particle is very heavy. It is like the nucleus of helium. 4 unit positive charges. A proton is 1 unit positive charge. An alpha particle is like 4 protons. मोटा है वो. And still the nucleus could hit it back. And it was the nucleus of what? Gold. Gold's mass number is in 100 above. You can Google and see. AU. I mean, let me see. AU. Gold's mass number is 196, 198. Much higher. So if you roughly divide 198, around 85, 98 protons are there in gold. This is the story when we don't know about neutrons. We have around 98 protons in. So gold's, what is gold's atomic number? Gold's atomic number AU is 79. So it has got 79 protons. So that 4 proton body came in, hit a 79 proton body. That छिटक जाएगा ना वो. It was like collision with a Rambasur. Kapak. Okay. So are we ready to understand the next phenomenon? Again, in your book, it will be written in one line. I never believe ऐसे जानना चाहिए. आइए. So now here you pay attention. Charge particle. Charge particle. See, at that time, it's not that people in the world are only studying about electrons. Somebody is studying electricity, somebody is studying electromagnetism, somebody is studying electromagnetic induction. A lot of studies are going on and theories are coming up, okay? Charge particles. By now, what all charge particles you know? You know an electron, you know something about a proton, okay? You also know something like an alpha particle, okay? You know an alpha particle. You also know a beta particle. Yeah, these are charged particles. right? Now this will bring in physics of first chapter R. So let's see. So let's say there is a center out here, and this is a circular track, and I have put here something which is a charged particle. If a charged particle or any particle undergoes circular motion is accelerated motion. Do you agree or not? Because the velocity every time is changing, right? Though the magnitude is not changing right now, what is the direction of velocity? This is the direction of velocity, right? After some time the particle will be here, and then we will say what is the direction of velocity? This is the direction of velocity. The magnitude may remain the same, but the direction of velocity is changing. If the direction of velocity is changing, then a charged particle, any charged particle undergoing what you call circular motion can be construed as accelerated motion. Accelerated motion. इतना समझ में आया कि नहीं? Circular motion is an accelerated motion. Now, if a charged particle is accelerated, this is what happens in your microwave oven. When your microwave oven gets bad, then the technician will come, and major part of the microwave oven is something which is known as a magnetron behind that microwave oven. The magnetron will get bad. The magnetron's job is to accelerate the charged particle. Have you seen MRI in hospital being done where the body goes inside tunnel? So they will first strip you of any magnetic. You cannot take anything because that will spin out there. Okay. So a charged particle undergoing circular motion is accelerated. Whenever a charged particle gets accelerated, it will release what is known as electromagnetic waves. And microwaves are a form of electromagnetic waves you have studied. So your microwave oven, that's why cannot take anything metallic. The moment the microwave oven is closed, the electrons will be accelerated inside it. A charged particle is accelerated. So it releases electromagnetic waves, which are nothing but forms of energy. Light is a form of energy. Light is only the visible part of the spectrum. If you have forgotten, Gadi X UV in my range. Hai The portion from here to here is what you see as light. The entire thing is known as the EMS, the electromagnetic spectrum of sound: gamma, X-rays, UV, infrared, microwave, and radio waves, right? So this Gadi XUV in my range. That's the best way to remember it. And this portion is light. A microwave is happening here. That is also radiation. So whenever a charged particle undergoes a circular motion, it will be accelerated, and if it is accelerated, it will start releasing something which is known as radiation, which is known as energy. All right? Now a bad example, but that is the way you will remember. Example thoda sa ganda hai. It's like viewer discretion advised. Suppose an animal is running circularly around a pole, and somebody just slits the throat of that animal. The animal will be oozing out blood. If it oozes out blood, will it not start losing its energy and life? So do you think that the motion will be circular? The motion will not be circular. Slowly the motion will be spiral. And spiral. That much you remember. Now let's go back to our story. This is the planetary model. Okay, so let me draw one more diagram that will make it better. So let's say this is the nucleus, and I have a big orbit, and he said that electron is a charged particle. It is undergoing what? Circular motion. Therefore the electron undergoes acceleration. As a result, the electron will emit energy, and if the electron starts emitting energy, the electron will start losing its mass, also energy, whatever, and it will slowly start following a spiral path. I am negatively charged and center is positive, so I'll come and tapak hit on the center, because I'm at the end of the day what? Negatively charged. This is positively charged. Huh. This thing, this entire phenomenon you will study later in electromagnetic waves also. This was given by, this was proposed, and this was known before that. This was proposed by James Clerk Maxwell. So we say, as per Maxwell's theory, a charged particle undergoing a circular motion undergoes an accelerated motion and should lose radiation or emit radiation, and as such is not capable to follow a circular path, should follow a spiral path, right?
He adapted towards the positive charge and just
It's moving, na? It moves. So if you move, you're losing energy in continuous rate. His idea, we have to go by what he said. He said it moves in fixed orbits. So it will, if it is moving, still it will be losing its energy. And as you are losing energy, you are being pulled also. So you might first ask me a question, why was I not pulled instantaneously? Because this is positive. No, because that is centripetal force acting on you. Take a bucket of dal, small dal, and rotate it. No box of dal. When you put yourself on a merry-go-round, you feel like flung out. That force, and that is in your chemistry 11, that is the first calculation you will do. What is the speed of an electron orbiting? The centripetal force, which is given by mv square by r, should be equal to the electrostatic force of attraction. Then only it will remain in orbit. And if the electrostatic force increases, right? Now what happens? mv square by r, the m is going on reducing. Throat has been slit, na? The mass is reducing. So the centripetal force is giving away. However, the electrostatic force of attraction remains the same. So it is now winning the battle and it is pulling you back. So we say the first thing, the first limitation, or which is said as drawback, is Maxwell's theory says that any charged particle undergoing circular motion undergoes accelerated motion. Electron, being a charged particle, also is undergoing, as per Rutherford, undergoing circular motion, which is an accelerated motion. And a charged particle undergoing accelerated motion radiates energy. That means it loses energy. As such, it cannot maintain a circular path, but will follow a spiral path. And finally, collapse at the center. The electron should come and collapse at the nucleus. So this is known as, this they coin is that Rutherford, we say Rutherford could not explain the stability of an atom. And here you should give your explanation. What is the stability of the atom? So here you have to bring the Maxwell story. The Maxwell finding versus Rutherford's model. I won't write it. I hope you have understood Rutherford's model. I'll just give you the outline of the story. Electron, charged particle. Hey, Alexa, stop. Electron, charged particle. So, charged particle, circular motion, accelerated, loses energy, spiral, collides at nucleus. It doesn't collide, huh? Means it should collide at nucleus as per this story. This is the problem. It doesn't collide, no. Atom stability is there. You gave me a model, and as per your arguments, the stability of the atom is not defended. He's an atom. He is stable. But as per your findings, I am countering that as per your findings, stability is not established. But he is stable. That means what? You're finding there is something wrong. This is the major drawback of Rutherford's model of atom. So Rutherford's model of atom will be now superseded by Bohr's model of atom. so many models सीखोगे तभी ना आप समझोगे